If the universe truly emerged from nothing, then what exactly is that nothing? Close your eyes for a moment. Try to imagine what you think nothing is. Maybe you pictured a perfect vacuum. No matter. No radiation. Just empty space. But now try to imagine something stranger. A vacuum with no matter, no space, and no time. What would that even look like? It sounds impossible to grasp, because it has nothing in common with the world we know. So our minds struggle to understand what nothing really means. In the book of Genesis, the Bible says that, "In the beginning God created heaven and earth." But what existed before creation? If time didn't yet exist, could space exist at all? The Bible offers no clear answer. And science, surprisingly, arrives at a similar mystery. Modern research shows that the universe is not eternal. Observations suggest that around 14 billion years ago, the cosmos exploded into existence. So what happened before the universe was born? Cosmologists have proposed many tempting ideas. Maybe our universe emerged from an older one. Maybe it's part of an endless cycle. Maybe it formed when two universes collided. And then there's the most unsettling proposal. The universe came from nothing. If that's true, how does something arise from pure nothingness? To explore that, we begin a journey through time and space. From the universe's first moments to its distant future, we'll dive into quantum mechanics, see how it shapes reality, and how it may lead us towards the greatest unanswered question of all. Where did the universe come from? Chapter 1: When Physics Changed Forever. In the early 20th century, physics was being rewritten. A young scientist named Werner Heisenberg was trying to understand atoms. He knew electrons orbit the atomic nucleus, but if they orbited like planets around a star, the atom should collapse instantly. How, then, do electrons actually move? What laws govern such tiny particles? Heisenberg tried every mathematical trick he knew. Nothing worked. Then, suffering from hay fever and exhaustion, he escaped to Helgoland, a windy island in the North Sea. One night, sitting on the rocks under the stars, inspiration struck. He realized something revolutionary. We don't need to know an electron's exact path, only the probability of where it might be. This insight shattered classical intuition and reshaped our entire understanding of the microscopic world. But Heisenberg's breakthrough had roots in a much older idea. Back in 1900, Max Planck tried to explain why hot objects glow. Classical physics failed completely. So Planck made a daring proposal. Energy isn't continuous, it comes in packets. Quanta. That tiny idea launched a brand new science, quantum mechanics. By the 1920s, with contributions from Schrödinger and Heisenberg, quantum physics matured, and the microscopic world became far stranger than anyone imagined. Matter wasn't fixed or solid anymore. It existed as probabilities, waves of possibility. Heisenberg stopped searching for precise electron orbits. Instead, he calculated where electrons were likely to be. An electron was no longer a tiny marble. It was a fuzzy cloud of uncertainty. Pin down its position precisely, and its speed becomes unknowable. Measuring its speed precisely, and its position dissolves into uncertainty. It was like trapping an electron in a tiny box. It bounces everywhere inside, but you can never know both where it is and how fast it moves. This became quantum mechanics' most famous rule, Heisenberg's uncertainty principle. It tells us that nature doesn't follow our everyday logic. In the quantum world, every measurement has a built-in blur. Even if you freeze an electron at absolute zero, quantum mechanics prevents perfect stillness. It must always tremble with a little energy. But uncertainty affects more than position and speed. Energy and time are linked the same way. Energy can fluctuate, appearing and disappearing for tiny moments, almost violating conservation of energy. That means even empty space isn't truly empty. The vacuum is filled with quantum energy, a restless ocean in which virtual particles, flickering in and out of existence. So nothing isn't nothing at all. It seeds with hidden structure and energy. Even today, Heisenberg's principle is one of quantum physics' pillars. but if you try to apply it to our everyday world, it makes no sense. Reality looks stable, orderly, predictable, but the quantum world lies underneath everything, and soon, we'll see how it shapes stars, galaxies, and even life itself. Chapter 2. When the sun was a god. Long before science, humans worshipped the sun as divine. Ra in ancient Egypt, Helios in ancient Greece, but they didn't know what powered it. Only in the 19th century did science attempt an answer. Lord Kelvin, the man who gave us absolute zero, tried to calculate how long the sun could last. Using the physics of his time, he assumed the sun's energy came from gravitational compression. He estimated that the sun could burn for no more than 100 million years, maybe 500 million at most. That terrified geologists and biologists. Earth's landscapes and life seemed to require far more time. Kelvin simply didn't know the secret locked inside atoms. Only in the 20th century did scientists discover that atoms contain a tiny nucleus, packed with protons and neutrons, to bind protons together, which naturally repel each other. Nature uses an unimaginably strong force, the strong nuclear force, smashing nuclei together, and you unleash staggering amounts of energy. Soon, physicists began colliding atoms, extracting their energy experimentally. Then Cambridge astronomer Arthur Eddington connected the dots. Stars shine because hydrogen nuclei fuse together. By the 1940s and 50s, driven partly by wartime nuclear research, scientists cracked the stellar code. Hydrogen fuses into helium. Helium fuses into carbon. Heavier elements build step by step. But ordinary stars cannot forge elements heavier than iron. For that, you need the giants' monstrously large stars, whose cores reach impossible temperatures and pressures. Those heavy elements, iron, gold, uranium, form planets, bodies, technology, civilization, but they remain trapped until a star dies. Only when a massive star reaches its final moment does it violently eject its treasure into space. And hidden in that violence is a ghost-like particle that almost never interacts with matter, the neutrino. Neutrinos have almost no mass. They carry no charge. They ignore electric and magnetic fields. They barely feel the strong force. They respond only to the weakest of nature's forces, the weak interaction. Wolfgang Pauli proposed their existence in the 1930s, but because they rarely interact with anything, they were indetectable for 25 years. Chapter 3. The wave function of everything. To understand neutrinos and everything else in the quantum world, we must understand the wave function. The wave function doesn't tell us where a particle is. It tells us where it might be. But here's the shock. Multiple particles don't each get their own wave function. One single wave function can describe all of them together, linking their behaviors in ways that defy common sense. So physicists wondered, could a single wave function describe the entire universe? Every photon, every atom, every ounce of energy, all encoded in one cosmic probability map. If that were possible, we could in theory know the position and speed of every atom and photon at a given instant. Classical physics would say, with that information, the future is fixed. The universe is a clockwork machine. But quantum mechanics disagrees. Today's wave function leads to tomorrow's wave function, but not to a single future, to many possible futures. Physicists didn't know how to choose the real ones. So in the 1950s, a bold young theorist made an outrageous suggestion. Hugh Everett III proposed the any-worlds interpretation. There is no single future. There are countless futures. In some universes, you won the lottery. In others, you are a rock star, or a famous actor. And in others still, nothing changes at all. Everett's idea was too radical for its time. He was ignored and eventually left physics. But the idea lived on. Even Stephen Hawking wondered if a quantum universe could solve the deepest riddles in science. Did the universe have a beginning? Hawking and Jim Hartle suggested that in the earliest universe, time had no definite meaning. Only when the universe cooled and stabilized did time switch on. To understand that quantum birth, we must return to the first instant, even to the first trillionth of a second, when temperature and density were unimaginable, and physical law itself began to crystallize. Chapter 4: Inflation and the Seeds of Creation. In the 1970s, physicist Alan Guth faced a strange puzzle: the mystery of magnetic monopoles, magnetic equivalents of positive and negative charges, which theory predicted, yet no one had ever seen. Guth suspected that in the universe's earliest instant, the laws of physics were simpler. Electric and magnetic forces were unified. If monopoles were expected, where were they? Guth proposed a stunning answer. Maybe the universe expanded at unimaginable speed, an event called cosmic inflation. As he worked through the equations, he realized inflation solved much more. It explained why the universe looks smooth and uniform across billions of light years. Inflation stretches tiny regions of space into enormous scales. Whatever smoothness existed at the beginning gets magnified across the cosmos. But inflation did something even more dramatic. Quantum fluctuations, Heisenberg-style uncertainty, would constantly create tiny ripples in space. Inflation froze those ripples into place, scattering them across the universe. When inflation ended, leftover energy poured into matter and radiation. Those frozen fluctuations created tiny variations in density, seeds that gravity magnified into the first stars. Which leads to a bold thought: is the universe just one giant quantum fluctuation? In 1973, physicist Edward Tryon stood up during a lecture and proposed a daring idea. Maybe the universe is just a vacuum fluctuation. Months later, he published a paper titled, "Is the Universe a Vacuum Fluctuation?" He wondered, if quantum energy can violate conservation briefly, what about the universe itself? Could the universe's total energy sum to zero? Positive matter balanced by negative gravitational energy? If so, the universe might arise from nothing, a quantum blip that never collapses. But that raises a deeper question. If time and space don't exist, what does it mean to fluctuate? This mystery lies beyond today's science. But one thing is clear: quantum mechanics shaped the universe's birth. Chapter 5: A Universe Growing Old. As the universe aged, it forged stars at a furious pace. Half of all future stars formed in the first few billion years. Most of the rest formed over the next 9 billion. Now star formation is fading. Only the smallest remaining 5% of stars will ever ignite. And stars are not forever. Massive ones burn out in millions of years. Suns like ours last billions. In the distant future, only tiny red dwarfs will remain, burning slowly for trillions of years. Eventually, even they will fade into cold embers. The universe will darken. Energy will drain away. Gravity will crush stellar corpses. But quantum mechanics pushes back. Heisenberg's uncertainty forces electrons into unpredictable motion. As they are squeezed, creating degeneracy pressure that halts gravitational collapse. Dead stars become eternal black relics. But even they are not immortal. Some theories argue that protons may eventually decay. Over timescales of trillions of years, matter might dissolve. Black holes might swallow everything. But not even black holes can escape quantum law. Stephen Hawking showed that quantum vacuum energy lets black holes evaporate, slowly emitting particles until they vanish. Even the mightiest structures in the universe are governed by uncertainty. Chapter 6: The Dream of a Final Theory. In 1958, physicists were electrified by an idea: a theory of everything, uniting quantum mechanics and Einstein's gravity. For decades, scientists sought a framework that could merge curved spacetimes with quantum probability. It was thrilling. Maybe this theory could reveal ultimate truth. Wolfgang Pauli came to Columbia University to present his unified vision. Princeton scholars gathered eagerly, but as the lecture unfolded, the room grew silent. The theory had hit a dead end. Geniuses had spent lifetimes chasing this dream. When Theodor Kaluza unified electromagnetism with relativity, Einstein was ecstatic. But as quantum complexity grew, that excitement faded. Einstein never stopped trying. Near the end of his life, he wrote, "Most of my intellectual offspring have died in the graveyard of lost hopes. Even today, progress has been slow." Quantum field theory explains particles beautifully, but cannot merge with relativity. Maybe the universe is built from strings, vibrating energy that forms matter. Maybe looping quantum gravity is right. Spacetime is woven from discrete loops. After a century of searching, no one knows which road leads forward. But imagine we succeed. Imagine we uncover a true theory of everything. A single law uniting gravity and the quantum world. Perhaps the Big Bang wasn't unique, just one bubble among endless universes. Perhaps time is not linear, but tangled, overlapping, multidimensional. Perhaps black holes aren't dead ends, but gateways to other regions of spacetime, or to other universes entirely. Such a theory could introduce laws of nature that we've never dreamed of, opening a door into the deep architecture of reality. It wouldn't just tell us where we came from, it would show how we are connected to the universe's hidden layers. Maybe we'll never find it, but the pursuit itself drives science forward. Every discovery, every new theory, pushes us closer. That pursuit began with a question about nothing, about the strange world of quantum uncertainty. This tiny domain, seemingly irrelevant to daily life, might hold the key to the universe's grandest secrets. From the birth of stars to the death of everything, from our own existence to the universe's origin, quantum mechanics has guided the cosmos. It reminds us that our familiar reality is only the surface. Beneath certainty lies a world of mystery and possibility, and our journey into that world has only just begun.